So, we have nice sensitivity now, so what we can do with it? Are there applications for that? And I would like to show you only two applications we have run in our laboratory. The one is the detection of ultra-low concentration of trace elements. So it's even in the sub-PPQ, I learned today, so in the PPQ or PPT level. So it's even further down. And showing some isotope ratio measurements done at 1 ppt concentration level. So first example, very low detection limits. And what you see here is, which is unbelievable, especially when you come from element 1 days, it's more than unbelievable. So there we have a standard addition of 0.1, 0.2 and 0.3 ppq of thorium. Of course, we put thorium because in the environment we have in the factory in Bremen is not a very high clean lab, but with this element it's a nice element to deal with. So, looking at, for instance, the signal we achieve with the system with 0.15 ppq of thorium, and you see still a nice signal in the area of 16-17 pounds per second. So, calculating now the limits of detection by these measurements, you will find that the limit of detection is 0.005 ppq. And honestly, we have to look and Google and in Wikipedia to look what is the next dimension, and we learned it's ppqt, so it's parts per quintillion. So detection limits in the range of 5 parts per quintillion. As said 20 years ago, nobody, I think it was not in the Tiger requirements list. The next example I want to show is the determination of isotope ratios, that were done on a concentration level of 1 ppt uranium, so an U010 standard. And you see with the system you even achieve with the minor isotopes, so the 253 intensities in the range of 1,500 pounds per second. So it's from a counting statistic point of view already in a region where there are reasonable results. When you look at the results and a little bit about the element XR detection system, you will see why I'm doing this in a minute. So with the element XR detection system, you have the ESA, exit slit, a filter lens, the secondary electron multiplier with the dual mode, and a Faraday detector. The nice thing with this system is that you can achieve 12 orders of magnitude of linear dynamic range, even a little bit higher. The electronics is done in a way that you don't have any response or decay, which is jumping from a small intensity to a high and back without any delay. And the filter lens, and that's what I showed the example for, that's for discrimination of ions with the wrong angle or energy. What does it mean? This is to improve abundance sensitivity, and you may know abundance sensitivity is a fact which is caused by ions that make collisions in the analyzer with residual gas molecules. And there, by these collisions, they lose a little bit of energy, but also get a different, slightly different angle. And you can discriminate them by an ion orbital system, which we call the filter lens. So applying the filter lens in low resolution, which is on the element resolution 300, that's a solution we have used 200 ppb of thorium from a standard IRMM 036, where the isotope ratio 230 to 233 is 3.11 ppm. So on the right here you see it's a logarithmic scale without applying the filter lens, so you see a clear, let's say, background caused by the abundance effect on the high or very intensive thorium-232 peak. Applying a positive voltage on the filter lens, you see a significant improvement in the abundance sensitivity. It's even in the below mass 230, it's even 0. But it can be improved further. For that, we have a slit combination which allows flat top peaks in medium resolution. So at resolution of can also be used for precise isotope ratio measurements of sulfur, phosphorus, and other interfered isotopes. Applying this system, or this combination, and in combination with the filter lens, again in the logarithmic scale, you see the 232 peak and the peak for 230, already it's a little bit much clearer, separated from the background. But applying now the positive voltage at the filter lens, you clearly see that all the abundance effect more or less is done and is solved. So this means we have a contribution from the 233 peak, the 230 peak of 0.8 counts per second, and compared to the sensitivity of the 232 peak of 12 million counts per second, then we get an abundance sensitivity of 67 ppb, which is also for a sector field instrument very good performance. Looking at the ratio determined here, we got 3.1 ppm, and as I said, it was a standard of 3.11 ppm, so very nice result. Since we are celebrating the 25th anniversary of a genre, and Rebecca also used the nice comprehensive bibliography from a colleague of mine, Chuck Dowsett, in the US. So he is collecting all the publications and making statistics of them. And he prepared one for me. And this is the number of publications. Started with the introduction of the first sector field ICP-MS in 1998, which was the plasma trace from VG. The blue arrows here tell you the introduction of the element 2, element XR, and you see since the introduction of the element, the number of publications significantly increased. When you look at the total number of publications, so far it's 5,000, nearly 5,800, and summing up all the publications done with the element, it's 5,280 publications. So 90% of the publications are done with the element. This is a very special thanks to our customer, of course. So to conclude, I think sector field ICP-MS evolved significantly since the first introduction, and just comparing the numbers, 20,000 counts per second, and now 270 million counts per second per ppb. I think clearly demonstrate this, and this is what we achieved with the chat interface. And with the chat interface also we calculated the overall transmission for uranium, so it's not at the 10% of the TIMS, but coming very close, and it's 3%. And this is including the embolization. With this system, we can show that we can measure very low concentration when they are not blank limited, of course, and with detection limits even down to the PPQT level. Due to the high sensitivity, we also can measure isotope ratios at very low concentrations, and in combination with the filter lens, we have, for instance, for thorium, less than 100 ppb of abundance effect. And this allows the measurements of large isotope ratios, as I have shown in the example. So, and what then, the combination of all the improvements made since then, what all can be done, that depends mainly on you, on the customers, and I'm pretty sure we will see a lot of new publications just by the combination of the new developments I have shown. And with this,